All right, let's get started. Just a couple quick announcements. Homework number 1 is currently being graded. We'll get that back to you as soon as we can. One thing I'll mention, everybody settle. One thing I'll mention with just the sheer volume of people in the class, I probably will not personally hand the homeworks back because I'll just be sitting here, for 10, 15 minutes doing that. Instead, I'll probably just leave them on the cart outside my office and let you all get them at your leisure. But I'll let you know when they're up there. I'll also make sure and upload solutions like I have in previous semesters, so you'll have that. Homework number 2 is due on Friday. I'm not pushing that one back because after today you'll have everything that you need in order to get that one done. And then the application for graduation is due on Friday somewhere. So online, right? Online. All right. I'll check. I've been teaching back to back today, so I haven't had time today, but I'll check for you.
Send out like make a video.
You're not freshmen. My goodness. Your words. All right. So just so you know, today what we're going to do is a full-blown tension member analysis example start to finish. And then after this, I think you will have a little bit of a flavor for how we go about design. And so that's sort of how I'm going to approach this. Is I'm going to start off doing the full-blown analysis, and then we'll derive what we need for design. So I think this is a good place to start. If you recall, last time, first I think we beat gross and net area into the ground. I think by now you should be pretty good on that. Last time we discussed in pretty significant detail what you need in order to compute U-values, shear lag factors. And we're going to exercise that today in our example. But I wanted to start off on slide 114 because this is a nice sort of concise summary of all of the formulas that you need for tension members, at least so far. So we have gross section yielding, which is our one of our 2 primary limit states. The other is net section fracture. Remember, the code lists that the formula is 0.75 FUAE for net section fracture, but AE is just our net area times the shear lag factor, so just do it all at once. There's really no need to compute an effective net area separately. Now, net area, remember it's the gross area minus the area lost due to bolt holes plus any necessary stagger factors. We have our shear lag factors. Remember, case 2 is the one that we're probably going to be employing more often than not for just about any problem that we analyze. And then our slenderness limit, L over R, has to be less than or equal to 300. Now we're going to add to this later with design expressions, block shear, threaded rod design, but so far this should be a nice little summary of all the formulas that you need for tension members. So with that, let's do an analysis example. So I want to determine the design axial capacity of the following tension member, and I also want to determine if the member meets recommended slenderness limits. So it's a 40-foot long W section. It's a W8 by 24. It's made of A992 steel, and it's 3/4 inch diameter bolts. Okay. So I have here an image of the fabrication or the fabrication details. So I have a cross section, and I also have an image showing the elevation view, if you will. So you can see the length of the connection. You can see the connection configuration, etc. Everybody okay with this? I'll give you a sec to copy all of this down. Does everybody have all the text from the slide? Because I've got the figure here in the notes. Okay. Okay. So here's the section. Now it's a W8 by 24, so we're going to need some section properties for a W8 by 24. Now I'm going to walk you through what you need for this problem, but I want you to recognize that it's very possible when you're doing these problems, let's say like on homework, that you look up a property and then you do some math, you go, oh crap, now I need this. And then, oh dang it, now I need this property. So you might have to go back and forth when you're doing homework until you get the hang of this, and that's just part of learning steel design. So is what it is. Now, I'm going to tell you what I need, but you're going to give me the values. So let's start off with the gross area. Somebody give me the gross area of a W8 by 24.
7.08.
7.08 inches squared. All right. How about the flange thickness? Somebody else. Don't be shy. 0.400, right? All right. Now, it might not sound like you need it right now, but I want you to give me the flange width. Somebody else. I see some folks in here without manuals. Say it again. All right. I'm going to need the depth. Somebody else. 7.93. Now, we're only going to need one of them, but I'm going to ask for both. I want somebody to tell me what Rx is, and somebody to tell me what Ry is. Let's start off with Rx. 3.42 inches. And what about Ry? Somebody else. 1.61. And all these came from table 1-1. Now, we're only going to need one of the R values because we're only going to use R minimum. But remember, for wide flanges, Ry is always the minimum. And I kind of wanted you to see that. When in doubt, just look them both up, okay? Now, help me out. What else do we know about this wide flange? Apart from, obviously, the dimensions and the spacing between bolts, what else do we know about this wide flange? The type of steel. What type of steel is it? It's A992 steel. So can somebody tell me what can we determine about A992 steel? The yield stress and the tensile stress. It's not the force, it's the stress. So somebody help me out. What is the yield stress for A992 steel? 50 KSI. And what is the tensile stress? 65 KSI. And where did you get that? Table 2-4. So now I'm going to wait. I'm going to make sure that everybody can find that. Everybody see that? Those tabs are starting to sound pretty valuable, aren't they? If you have not yet started to tab your manual in these specific sections, I would do so. This table, table 2-4, you're going to be turning to this table for the rest of the semester. This is probably one of the most referenced resources that we use in steel design, period. Sound good? Okay, now, there are two limit states so far that we need to assess tension members according to. What are they? Two limit states. We have gross section. There we go. Gross section yielding and net section fracture. Let's take them one at a time. Let's talk about gross section yielding. What do we need in order to determine the capacity according to gross section yielding? What do we need? We need the yield stress and we need the gross area. Do we have those? Let's just go ahead and do it now. So gross section yielding. The alpha. That's phi. That's the resistance factor. So remember in concrete design, remember how we had phi mn? So this is phi pn. So this is a factored axial capacity. For those of you that are in concrete design, today we just looked at mn, the nominal moment capacity. So pn would be our nominal axial capacity adjusted by phi to get a design value. So ultimately what we're computing is a phi pn. Because there's two different limit states. For each, that's a good question. For each limit state, there is a design capacity. It's all about which one controls. That's a great question. Yes, and you'll see what happens here in a second. And let's not forget that there's going to be a third limit state later when we look at block shear. We'll have to look at block shear later. So, all right. So, what's our formula for gross section yielding? So the FYAG, that's our nominal capacity, and 0.9, that's our resistance factor. So 0.950 KSI times, what was AG, 7.08? And so phi TPN equals what? 318.6. First off to the number. Do I have a second on that? And what are the units? Nope. Kips. So I propose that I get this tension member, this 40-foot long W8 by 24, and I start yanking on it, it experiences yielding at 318.6 kips, adjusted by resistance factors. So this is our design axial capacity according to the limit state of gross section yielding. So if gross section yielding was all we needed to consider, all we need to do for this tension member is ensure that the factored load is less than that, okay? But that's not all we need to consider. We also have net section fracture. Can we go ahead and compute net section fracture capacity right now? Why not? And what else don't we have? What is AN? It's the net area. We don't have the net area, right? We got a lot to do before we get to net section fracture. So gross section yielding, that one's the easy one. We got to do net section fracture. And so the first thing we need to do, let's look at net area. Now, let's be clear. In general, net area is defined as the gross area minus the area loss due to bolt holes plus any necessary stagger factors. We don't have to worry about stagger factors on this problem? Or does it look like it? No, there's no diagonal bolt pass or anything like that, so we ain't got to worry about that. So let's talk about that. So gross area minus the area lost due to bolt holes. Let's talk about the bolt holes. What do we know about the bolts? So if the bolts are 3/4 inches in diameter, what does that mean? The holes are 7/8. What's that? No, I actually think here recently that they've corrected that, but let's revisit that when we get to bolted connections. So, because I think they just released a version of the manual here recently that corrected that, but correct me, but we'll see. We'll see. All right. We have the hole diameter. Help me out. How many holes do we need to subtract? Bless you. Say it again. How many holes do we need to subtract from this cross section? 4, right? Here's the cross section. Samurai sword or lightsaber. We're cutting through 1, 2, 3, 4, right? Okay. And what is the area of that hole? It's the diameter of the hole times what? The thickness of what? Do we have that value? Yeah, I had you look it up earlier. See, it's like I'm not completely crazy. So I propose then that the net area is the gross area minus 4 times the diameter of the hole times the flange thickness. Oh, that's a little far. So that is 7.08 square inches minus 4 times 7/8, and then the flange thickness, that was what, 0.4? And so what does that come out to be? 5.68? Square inches, right? That's an area. That's always the case for a rolled shape. Always the case for a rolled shape. Now, the flange and the web are not going to be the same thickness. Now, if we were talking about, let's say, a plate girder where you're actually taking a plate, and manufacturing a girder, yes, they can be different thicknesses, but not for rolled shapes. No, I mean, they probably could, but they don't. I mean, they're mass-producing shapes, so they're producing ones that are symmetric. So, I mean, yeah, it's probably within their possibility, but it's really never been brought up. So, everybody good? Now what? What do we need? Shear lag factors. So, all right. So we need to refer to table D3.1, right? Let's turn to table D3.1. All right. Is case 1 going to be applicable for our cross section? Why not? What's the difference between case 1 and case 2? That's exactly right. There are no bolts in the web. If the web was bolted, then we'd be under case 1. But we have a situation where the flanges are connected, but the web is not. So we are going to consider case 2 for sure. So let's look at case 2. So what is the formula for case 2? And remember, those are the connection eccentricity and the connection length. Let's take those one at a time. How do we determine the connection eccentricity? Somebody over here. How do we determine the connection eccentricity? We have a W section connected via the flanges. Everybody remember that? There we go. So we have the X bar for a W8 by 24. And so what we need is the Y bar for a WT what? Y'all remember this? Say it again. 4 by 12. So what is the Y bar for a WT 4 by 12? Remember this? Remember, if you have a W section connected via the flanges, you use the equivalent WT that's half as deep and half as heavy. Y'all remember that? So if you have a W8 by 24, that's a WT 4 by 12. Remember that? So what is the Y bar for a WT 4 by 12? Remember, we don't look up Y sub P, we look up the Y bar. So what is the Y bar for a WT 4 by 12? 0.695. Did I write that too small? Which one? It's X bar, so it's X bar sub CON. And that's just W8 by 24 and WT 4 by 12. Now, is everybody able to find that value? Everybody that has their AISC 15th edition steel construction manual with them? I see some people like, I don't know what you're talking about. Everybody good? Now, what about the connection length? How do we define the connection length? The center to center of the outermost bolts, right? So what is that? So remember, we're looking for this dimension here, out to out on the center to center bolt spacing. So what is that for our problem? Let me go back, let me skip ahead a little bit. 9 inches, right? It's not 11. It's 9, okay? We don't consider this little bit, okay? Everybody okay with that? Make sure you're clear on that. You don't. You don't cut it in half. All right? If you have an angle, remember, that's what this slide's for here, this slide 106. If you have, let's say, a long-legged angle, or like it's connected by the long leg, then just the X bar for that angle. If you have, let's say, a channel connected via the web, it's just the X bar for that channel. The WT, the equivalent WT, is only for W shapes. It's a specific special case. So that's a good question. Everybody else okay with this? All right. Now, if you're okay with that, would you agree then that U sub 2, and I'm calling it sub 2 because it's case 2, would be 1 minus 695, sorry. One over 0.695 over 9, and what's that going to be? We'll say 3 decimal places. 0.923. Do I have a second on that? Now, that's case 2. Is that it? What's that? Well, you tell me. Are there any other cases that would be applicable? Remember, with shear lag, you could have multiple cases. I'm making you read. It's like we're engineers. We don't want to read. Case 7. Everybody see that? What does case 7 state? A W, M, S, or HP shape or T's cut from these shapes. And then if you look at the upper case along that, it says with flange connected with 3 or more fasteners per line in the direction of loading. Is that the case for our section? How many fasteners per line for our shape? 4, right? So is that case applicable? What? 3 or more. We have 4, right? Yeah. Yeah, now this is the flange and it has 3 or more, right? Because remember, here's our section. Here's our section. We have 1, 2, 3, 4 fasteners per line because that's in the direction of loading and it's in the flange. Now, how do we determine what our shear lag factor is according to case 7? There we go. So what was BF? And what do we compare that against? No, 2/3 of D. So what is 2/3 of D? Is 2/3 of 7.93. And so that's 5.29 inches. So comparing BF and 2/3 D, BF's bigger. So what's our U value according to case 7? 0.9. Now, which one do we use? U2, right? Read that note on case 7, and what does it say? If U is calculated per case 2, the larger value is permitted to be used. And again, that's just because it fits the test data more closely. All right? So therefore, U is 0.923. Now, do we have everything we need to compute net section fracture? What do we need to compute net section fracture? We need FU. We got that? What else do we need? We need net area and U, right? We got everything we need. So and so what does that come out to be? We'll just say 1 decimal place. So 255.6. The second on that? $255.6 what? Kips. So, to summarize, at least to summarize so far, this came out to 318.6, and this came out to this. So if I was yanking on this, which load would I hit first? Its capacity according to gross section yielding or its capacity according to net section fracture? Net section fracture. So what you were saying, do you take the lowest one? Yeah, you take the lowest one. So I propose that the design capacity of this section, the phi PN, is 255.6 kips. Now, we got one other thing that we got to look at on this problem, and that's slenderness. But before I do that, I want to sort of go off to the side a little bit. So I'm sure that there's some of you that are like, great, phi PN is 255.6. Who the hell cares? What does that mean? Okay. Well, I'd like to provide a little bit of a sort of a reality dose so that you can kind of see what's going on. Let's say, for the sake of discussion, let's say, for the sake of discussion, that this member is subjected to an 80 kip dead load and a 90 kip live load. And let's say that these are service loads. Y'all remember what service loads mean? It means that it's unfactored. Okay? So what I will then do is, let's say I've got these service loads. What do I do to this dead load and this live load? Say it again. There we go. So we need to factor them. And if all you have are dead loads and live loads, the controlling load combination is as follows. And so what do you get? Say it again. What would that mean for this section? It's safe, right? The factored load is less than what it can withstand. But what if this number came out to be 340? It's not safe. So what do we got to do? Beef it up, right? So after this, once we get finished with this example, maybe our next question is, how do you select a member to safely resist loads? And you know what they call that? They call that design. So structural steel design. Oh. But we're not quite done. We got one other thing to check, and that's slenderness. Now, how long is this member? Now, what was my minimum radius of gyration? But which one was that? RY. Anybody see a problem? Units. 40 feet is how many inches? That was actually really bad. Is that better? No, it's okay. It's okay. That would that's a cop out. No, I'm gonna write it out. Hold on. 480 inches. There we go. It looks like an M. I know I did, but not now. It only goes so far. So L over R is going to be 480. Yeah, and I'm just going to write the tick marks. 1.61. What does that come out to be? 298? What does that mean? It's just barely good enough. So this member is real slender, but it's good. Any more, and we'd probably want to beef it up just for handling purposes. So this is less than 300, so we'll say member meets, I drew the E, meets, I know. Yeah, it just barely works, right? What do you think?
The 98 were at 200 that were wasting material. We want to try bracing.
Kind of. And I'm going to show you what I mean by that here in a second. But the answer is kind of. All right, hold on. Shh. His question was, if your L over R was really, really small, would that mean you were wasting material? And the answer is kind of. All right. Is everybody okay with this so far? Okay. All right. Now, you tell me, does everybody have sort of a general idea of what's going on with tension member analysis? The idea is, here's a tension member, right? Here's a tension member. What is its capacity? That's what tension member analysis is. And you can take that a step further and say, here are the loads. Is this tension member safe? It's still in the realm of tension member analysis. Now, I'd like to take it a step further. What about design? What if I give you some loads and I say, find me a member that works? Find me a member that safely resists those loads. That is tension member design. Now, I want to be absolutely crystal clear about real-world aspects and what we're going to do in here. Okay? In practical, real-world steel design, the goal is to obviously design the most economical system that you can. Okay, let's take this building. How many beams are in this building? A lot, right? Short answer is a lot. Okay. Now, imagine that every single individual beam was designed economically. So let's just make up a number. Let's say there's 800 beams in the building. Imagine being the contractor and have to put together a 5-story erector set with 800 different beams. Would you be a happy contractor? No, you would not. But imagine that instead, as the structural engineer, I use maybe, let's say, the same 5 shapes over and over and over again. Maybe some beams aren't as economically designed as others, but in the end, the whole system is economical. Does that make sense? It makes a little more sense in the long run that you might actually be sizing an element that's a little bigger than it needs to be, because in the big picture aspect, that design makes sense. Okay? So the point I'm getting across is I don't want you to think that the lightest shape is always the most economical in big picture aspect, because sometimes it isn't. For our purposes in this course, however, when we're doing design problems, we're going to use the lightest section as our metric as to whether or not the problem is correct or not. In other words, if I give you a design problem, the goal is to always pick the lightest section. So how do I know how heavy this section is? Which number tells me what's the weight? The 24. So if I give you a design problem and I say pick the most economical W8 section that there is, I want you to pick the lightest one, the one with the smallest weight, the one with the smallest 24 value. Everybody okay with that? So that is generally going to be a metric that we use throughout this semester. Okay? The eternal battle between architects and structural engineers. We can talk about that. Hey, they serve a purpose. They have to take this abstract idea from a client and turn it into some reality that meets fire code requirements, ingress and egress requirements. That's not easy. Just as we have to take their vision and turn it into something that isn't going to kill people. So that's not easy either. So the eternal battle. I want the building to float. Well, if buildings could float, I'd be out of a job. All right, let's review how we're going to design, and we're going to review these design procedures looking at each limit state. So let's start off with yielding in the gross section. Now I want to start off with this equation right here, okay? The idea that the resistance has to be greater than or equal to the factored loads. Okay? So factored resistance has to be greater than or equal to factored loads. Well, if we're talking about yielding in the gross section, what is the factored resistance? It's 0.9 FYAG, right? Well, if I'm in design mode, if I assume a given type of steel, what am I solving for? I'm solving for the gross area. I propose that the gross area has to be greater than or equal to that fraction. So this is a design expression. Got a problem? Got some loads? I can solve for a gross area requirement. What about slenderness? Well, L over R has to be less than or equal to 300. What don't I know in design land? I don't have a clue what the section looks like. But what I can do is solve and determine what section I need to use such that it has a radius of gyration less than or equal to L over 300. Or greater than or equal to L over 300, I should say. Sorry. So, going back to what you were saying, are you wasting material if you use a section with a really low L over R? That's not really how I would look at it. What I would look at it is this. I've got a design problem, and I have a limit on my gross area and a limit on my radius of gyration. So pick the first section that meets both of those limits. So one may govern, one may not. So you could have a section that's super slender but has buku gross area, or the other way around. More often than not, it's the other way around. But basically the idea is you've got multiple objectives that you need to meet, and one of them is going to govern. Everybody okay with this? Now here's the thing. That's gross section yielding, and that's slenderness. What about net section fracture? That one's complicated. That one's complicated because, think about it. In order to compute the capacity according to gross section yielding, you need to know what the shear lag factor is, right? You need to know what U is. You also need to know what net area is. Well, how the heck do you know what net area is if you don't know what the thickness is? Keep in mind, this is design mode. You don't have a clue what the section looks like because you're picking the cross section. So how do you go about this? How do you go about design if you have no idea what a U value is and you have no idea what the thickness is? How do you do that? There's too many variables. The answer is you recognize that there's too many variables, and you guess. Okay? So I propose that a reasonable guess for the purposes of design is to assume that the effective net area, that's AN times U, that the effective net area is about 75% of the gross area. So that's going from the gross area to the net area, and then taking the net area and adjusting it by the shear lag factor. I propose a reasonable guess is that that's about 75%. It's a guess. It's a guess. But we got to start somewhere to get a section worth investigating. So if we plug that in here and we solve for the gross area, we get the following expression. Now, why do we have 0.75 squared? Well, we got 2.75 floating in there. One of them is our phi value, and one of them comes from this assumption. Okay? Everybody all right on this? So think, if we have, let me go back. So we have one limit on gross area. We have another limit on gross area. So what I propose is let's just combine those into a single expression. And so in design mode, what we'll do is we will compute a minimum gross area, and we'll compute a minimum radius of gyration. And then we will pick a member that seems to work. Now, here's the thing. We are picking these members based on guesses, based on assumptions. We assumed the thickness and the U value in that 0.75. We just made a guess. We picked the value straight out of air, straight out of thin air. So we still have to check that guess. So we are going to use these equations in order to pick a trial shape. We will then take that trial shape and do exactly what we did in the previous example. We will analyze that trial shape in order to assure it's valid. Now, how do we know that that's the right answer? How do we know that that's the most effective choice? Well, there is a measure in structural engineering called efficiency. Let's go back to our previous example. What was the load? It was what, 240? The factored load was 240. What was the factored capacity? 255.6, right? What's the ratio of those two? What's 240 divided by 255.6? 0.938. Do I have a second on that? Okay. I propose that the efficiency of that member is about 93.8%. Okay? That's a very simple means of determining whether or not your design is efficient. A good rule of thumb is if your efficiency is 90% or greater, you're good. Okay? You're more often than not picking the section that is most economical. It's a rule of thumb, so it does not always work, but in this course and on exams and anything like that, if you compute an efficiency that's 90% or greater, you're good. Okay? So for our purposes, we can assume that's the most economical. So I don't want you to think, well, what if the efficiency is 90.2% and there's actually a section that's greater? Don't worry, it's fine. So I'm not going to do that to you. Yes? That's a good question. First off, it is like The Price is Right, you know, closest to 100% without going over, right? At least somebody got the reference. Now, as for whether or not is there a too close? Well, mathematically, I'd say no. I mean, if it's 99%, go with it. Now, a lot of practicing engineers would back it off a little bit, just in case a member gets, you know, dinged up during shipping or something like that. But keep in mind, you're not using raw loads. You're taking that live load and you're bumping it up 60%. You're taking that dead load and you're bumping it up 20%. Think net section fracture. We took the capacity and we multiplied it by 0.75. So there's a lot of safety factors built into that. So it's like once your safety factors are built into it, at what point do you say, you know, you can cut it off? So, you know, honestly, I'd say go with it. Now, let's also be clear, there are only so many rolled shapes in the manual. So the likelihood that you find a shape that is 99.999999999% is very low. Usually it's going to be discrete. So it's going to be, like 110, 105, and then 97. It's going to be discrete, so in practical applications. So. Sound good? Next time, we're going to design a member. Start to finish. So we'll actually do some steel design in CE 414. That's all I got, everybody. See you on Wednesday.